Thank you. Hi everyone. My name is Patricia Buffon. I am a PhD student at the TU Delft, and I will be presenting part of my research on turbidity currents triggered by water jets as a sediment management technique in water reservoirs. This is my presentation outline. And I would like to start by presenting the motivation of this study. So in this figure, you can see in blue the area of land that is drained into dams. And this shows us how important these structures are for our societies worldwide. And I also would like to show you a bit of the Brazilian context, which especially motivated this study. So this is data from the Horizon 2050 report. In black, you can see the current or in construction dams, and in red, you can see the potential ones. Nowadays, hydropowers represent 60% of the energy matrix, and we have a scenario of increasing water demand. Just so you to have an idea, for the next decades, it is expected that the demand of water for irrigation only will be up to 30%. Sediment trapping in these structures is the main reason that determines the lifetime of them. It also reduces the water storage capacity and then has a consequence energy production, flooding control, water supply. It also affects the fluvial and the coastal morphology and has a consequence the ecosystems. So to deal with sediment trapping in water reservoirs, sediment management strategies are applied. And there are a series of sediment management techniques that can be applied in these strategies. I will be talking specifically about water injection, which is a type of hydrodynamic dredging. In this picture, you can see the main processes involved in the application of this technique. So there is the water injection, then a scouring process that suspends the sediment, and it evolves to a turbidity current. And these processes, they can be divided in 4 spatial regions, injection, impact zone, near and far field of the turbidity current. My research question is what is the relationship between the jet boundary conditions and the boundary conditions of the turbidity currents? Knowing this relationship is important because the processes that happen in between the injection and the turbidity current are too complex and too difficult to model and to predict. And if we are able to establish a relationship between the jet characteristics and the characteristics of the turbidity currents that we are triggering, then we are able to predict these flows and optimize the technique both economically and environmentally. To study this, we built a physical model. So here you can see a picture of the flume. It has a 1 meter deep deposit built with plastic sediment. This white device is a diffuser, a hydrodynamic diffuser that reproduces a 2D jet. And you can also see the instruments that we used. So we are using ultrasonic velocity profilers, an ADV, and the conductivity probes to measure the concentration close to the bed. We also performed a bunch of experiments to characterize the jet and to confirm that it can be predicted accordingly to the planned turbulent jets theory. Here, there are other characteristics of the model, but what I would like to highlight is that for these experiments that I will show, we used a slope equal to 0. The jet was positioned with an angle of 45 degrees, and we simulated discharges from 1 liter per second up to 4 liters per second. To show the preliminary results, I will start with these two videos. So these are two different cases for 2 liters per second and 4 liters per second. So here you can already see that these flows, they behave differently. The bottom case has a higher velocity, higher concentrations. And what I also would like you to notice is that at the first moments of the experiment, this suspension rapidly evolves to a turbidity current. But with the increasing depth of the scarring, a vertical component develops here, which brings the sediment up, and then it plunges into turbidity current. And this means that the near field of the turbidity current is varying over time. I will get back to that later, but I wanted to highlight that. So here is a sum of the experiments. So for the case of 1 liter per second, we didn't trigger a significant turbidity current. Then for the other cases, as I explained, with increasing discharge, velocities and concentrations increase as well. We did not find the upper limit yet within the range that we can trigger turbidity currents. So we will keep increasing the discharge until we find this limit. So here it's just a plot showing what we would expect, that with increasing discharge, we increase the erosion rate. And here there are some, well, so on the up part, you can see velocity profiles in 3 different positions in the longitudinal profile for the 2 liters per second case, and in the bottom part for the 4 liters per second case. And this, so the time window that I am analyzing the data here is around the 200 seconds, and the profiles are averaged over 27 seconds, more or less. And what I would like to highlight is that mainly for these 2 upstream positions, we see over this period of 200 seconds approximately a quasi steady state of the flow, which is important for us because then we can derive statistics of the flow. So some conclusions. The methodology successfully triggers turbidity currents using a weather jet. This experiment was quite challenging to set up, and we managed to trigger a range of turbidity currents by simply changing the discharge. Still, we will keep increasing the discharge until we find this upper limit of the range. And it seems that the processes that drive the transition to a turbidity current, they change over time, but as I explained before, this does not seem to influence the turbidity current downstream, which is important for us because it means that even though we have this region between the jet and the turbidity current varying during the experiment, or downstream part is not affected by these variations, not significantly. For future work, we will obtain vertically averaged values. We will develop a relationship between the jet momentum and the near field of the turbidity current, so thickness, velocity, concentration, and possibly turbulent kinetic energy. And here I put a near field in red because, as I explained previously, the spatial definition of these regions, they are not so straightforward as we thought before. So we need to give it some more thought. And we will also investigate the effect of changing the impingement angle and the bed slope. And with this, I conclude the presentation. Thank you, and I'm happy to answer any questions.
Thank you very much, Patricia, for this presentation that contains beautiful turbidity currents. So for the audience, please put your questions in the question box so that Patricia can answer them. My first question would be whether you have also studied the distance at which the sediment was redeposited on the bed, or was the sediment actually taken out of the experimental domain entirely?
Not entirely, but yes, part of it was transport downstream. That's something that I will look more in detail now with the images. But we did have, for instance, bed forms formation. There is deposition over time. Overall, there is deposition, but in the first minute or two, the turbidity current seems to be more efficient, which makes sense because the scarring is not so deep. But there is a significantly quantity of sediment being transported downstream.
Yeah, fantastic. So a question coming from the audience by Zain Job. Great talk. I maybe missed this, but was there a slope at all in the experiment, or was it completely horizontal?
This one was completely horizontal. We decided to start with a zero slope to not complicate things too much. But now we will also vary the slope. This flume allows us to go up to 17 degrees, more or less. And that first we will change the angle of the jet, and then that will be the next step. We want to check what is the effect on the turbidity current.
Fantastic. Well, very much looking forward to those results.
Thank you.